dear students, we are on the CEC Gurukul lecture and we are in the series of the electronic circuit, and we have discussed the various electronic devices up to now. In the today's lecture we discuss the one of the important device, that is the thyristor, that is also called the silicon controlled rectifier, that is SCR. Basically thyristor is similar in the construction to the transistor, and it is a multi-layer semiconductor device. Hence, silicon part of its name it comes. It requires a gate signal to turn it on, and control part of the name, as it is called the on, and as we suggest that it is known as a silicon controlled rectifier. Silicon, why it is silicon in the part? Because we are using the silicon semiconductor and it requires the signal on and off, so we use it as a control. And why it is a rectifier? Because it behaves like a rectifying diode. So it is a silicon control rectifier. That is a part of the name. In fact, the circuit symbol for the thyristor suggests that this device acts like a controlled rectifying diode. Now, however, like the junction diode, which is a two-layer, that is the P and N diode. Now, here the semiconductor devices or the commonly used bipolar transistors, which is three-layer device. One is the PNP or NPN switching devices. The thyristor is a four-layer, that is PNPN semiconductor device that contains the three PN junction in the series, and it is represented by the symbol as is shown in the diagram. You see here, left hand side is similar to the diode, but here gate is attached. One left hand side is anode, right hand side is the cathode, and the gate is, because it is a three layer, that's why we use the gate here. It is a multi-layer. Like the diode, thyristor is a unidirectional device, and it will only conduct in one direction only. But unlike the diode, thyristor can be made to operate as either an open circuit switch or as a rectifying diode, which depends upon the thyristor gate which is triggered. In other words, thyristors can operate only in the switching mode and cannot be used for the amplification. So, thyristor we will use for the switching mode, on and off mode, in the control manner, where we use the silicon as a semiconductor, and it is work as a rectifying diode, and it is unidirectional like the other diodes, and it conduct the current in the one direction only. The silicon control rectifier SCR is one of the several power semiconductor devices along with the triacs, that is the triode ACs, diex, that is the diode AC, and UGTS, that is a uni junction transistor, that are all capable of acting like very fast solid state AC switches for the controlling the large AC voltages and the current. So, silicon control rectifier will use for the fast solid state AC switches, because to control the AC voltage and large AC currents. So, the electronic student that this makes these very handy solid state devices for controlling the AC motor lamps for the phase control. The thyristor is a three terminal devices, as we have seen in the diagram. Three terminal devices, one is anode, second is the cathode, and third is the gate, which consisting of the three PN junctions, which can be switched on and off at an extremely fast rate. We can on and off it with the speedily. We can change the high power current or high power voltage by using this thyristor. So, for on and off we can get the extremely fast rate, and can be switched on for the variable length of the time during half cycle to deliver a selected amount of power to a load. The operation of the thyristor can be best explained by assuming it to be made of the two transistors that are connecting back to back as a pair of complementary regenerated switches. As you see in the diagram that here the two transistors are connected base to base. Two transistor analogy. Here we see in the left hand side the full thyristor is shown, anode, cathode and gate, and which is made from the two transistors which are attached back to back. You see N and N are attached, P and P are attached. So in this manner we can get the layered arrangement PNPN PNPN diode combination. So this is the thyristor. As we see the two transistor equivalent circuit, which shows that the collector current of the NPN transistor TR2 feeds directly into the base of the PNP transistor TR1. Here we see that the PNP base just connected with the NPN base. Now you see the both are combined, while the collector current of TR1 feeds into the base of while the collector current of TR1 is attached to the base of the TR2. So in this manner we can connect these two transistors and we will form the thyristor. These two interconnected transistors rely upon each other for conduction, as each transistor gets its base emitter current from the other's collector emitter current. So until one of the transistors is given some base current, then nothing can happen if an anode to cathode voltage is present. So when the thyristor's anode terminal is negative with respect to the cathode, the center NP junction is the forward bias. When it will be forward bias, when the anode terminal is negative with respect to the cathode terminal, but the two outer PN junctions are reverse biased and it behaves very much like a ordinary diode. So the two junctions are connected. The two just to make the thyristor, the two PNP junctions are attached. Therefore, a thyristor blocks the flow of reverse current until its some high voltage level, the breakdown voltage point of the two outer junction is exceeded, and the thyristor conduct without the application of the gate signal. And this is an important negative characteristic of the thyristor, that thyristors can be unintentionally triggered into the conduction by the reverse over voltage as well as the high temperature or a rapidly rising dB by dt change in the voltage with respect to the time voltage, such as the spike. So we can get the spike in it. If the anode terminal is made positive with respect to the cathode terminal, the two outer PN junction are now forward bias, but the center NPN junction is the reverse bias. Now it is opposite. When the anode is negative, then the then the two PN junction forward bias, reverse bias in that case, but now here the anode terminal is positive with respect to the cathode, then the two outer junctions PN junction which are the forward biased, but the center junction, which is NP, is the reversed bias. Therefore, the forward current is blocked. If a positive current is injected into the base of the NPN transistor TR2, the resulting collector current flows in the base of the transistor TR1, and it will just collector current to flow in the PNP transistor TR1, which increases the base current of the TR2. In this manner, the forward bias, the TR1 increases base current of the TR2. Very rapidly, the two transistors force each other to conduct the saturation as they are conducted in the regenerated feedback loop that cannot stop. In this manner, they will continuously work. On in the diagram, we are seeing the one of the thyristor we generally use in the laboratories or in the electronic gadget. Now, when the trigger into the conduction, the current flowing through the device between the anode and cathode is limited only by the resistance of the external circuit, as the forward resistance of the devices when the conducting of the devices can be very low at less than 1 ohm. So, the voltage drop across it and the power loss is also low in this case when we trigger it. Now, the thyristor block the current in both the direction of the AC supply in its off states and can turn on state. Then it may to act like a normal rectifier diode by application of the positive current to the base of the transistor. Now, the TR2 which for a silicon control rectifier is called the gate terminal. Now, TR2 become a gate in this manner. The operating voltage or current can define the characteristics of the silicon control rectifier in the forward and the backward direction is here on the screen. We can see that here PNP, it is PNPN thyristor, and left hand side you see the symbol is positive and negative terminal, anode is positive terminal and cathode is a negative terminal. Now you see the current, how the current is flow. It is flowing from anode to cathode and gate is there. Right hand side you see the diagram how the current is flow as the voltage as the current flow, how we can get the voltage characteristics, IV characteristics in the forward direction and the reverse direction. And above we are having a forward direction, but at the lower side on the left hand side we have the reverse direction. Now here we have the holding current, and you see in the diagram that there is a there is a breakdown voltage, and after that we are having a holding current, and then we have the on state. Apart from this we are having the reverse voltage on the left hand side, that is a blocking voltage, and the reverse biasing is there. Then the reverse breakdown voltage on the left hand side, it work on the off state. You see here on and off state at the forward bias how it is working. The gate is there, that is triggered on, then that is the conduction is takes place as it will go forward. Then here we are in a off state, that is the forwarded voltage breakup. After that it again the breakup, then holding current, and then on state we will get in the forward biasing. Now one of the thyristor has been turned on and is passing current in the forward direction. When is the anode is positive, the gate signal loses all the control due to the regenerative latching action of the two internal transistors. So, the application of any gate signal or pulses after generation is initiated will have no effect at all because the thyristor is already conducting and is in the on state. Unlike the transistor, SCR, silicon control rectifier, cannot be biased to stay within the some active region along with the load line between its blocking and saturation state. So, the magnitude and the duration of the gate turn on pulse has little effect on the operation of the devices since the conduction is controlled initially. So, applying the momentary gate pulse to the devices is enough to cause it to conduct. So, when we just giving the momentary gate pulse to the devices, then it conduct and will remain permanently in the on state even if the gate signal is completely removed. It means the gate signal is used to trigger the devices. Therefore, the thyristors can also be thought of a bistable latch which is having the two stable state, one is on or on, other is the on, off and on. This is because with no gate signal applied, a silicon controlled rectifier which blocks the current in both the direction of the AC waveform, and once it is triggered into the conduction, the regenerative latching action means that it cannot be turned off again just by using this gate. So if we have a question that how do we turn off the thyristor, then when it is continuously on after giving the trigger to through the gate, then how we turn off the transistor. So answer is that the once the thyristor has self latched into its on state, passing a current, it can only be turned off again by either removing the supply voltage and therefore the anode current, completely reducing its anode to the cathode current by some external means to below the value commonly called the minimum holding current, and that state will be the off state. The anode current must therefore be reduced below its minimum holding level long enough for thyristor internally latched PN junction to recover their blocking state before a forward voltage, and is again applied to the devices without its automatically self conducting. Obviously, then of a thyristor to conduct in the first place its anode current, which is also its load current, that is IL, must be greater than its holding current value. It means IL greater than IH. Or we can say that the load current greater than that of the holding current, then we will get in the off state. Since the thyristor has the ability to turn off whenever the anode current is reduced below its minimum holding value, and it flows then that when used on the sinusoidal AC supply, the SCR will automatically turn itself off at the some value near to the crossover point of the each half cycle, and as we now know will remain off state until the application of the next gate trigger pulse. Since an AC sinusoidal voltage continually reverses in polarity from positive to the negative on every half cycle, this allows the thyristor is in the off state at the 180 0 point of the positive waveform. As we see that the curve is moving at the 180, that is a holding point where we can get the 180 0 point of the positive waveform in the forward bias, and this effect is known as the natural commutation, and it is very important characteristics of the silicon control rectifier. Basically, thyristor used in circuits fed from the DC supplies also, and this natural commutation condition cannot occur as a DC supply voltage is continuously, so some other way to the turn off the thyristor must be provided at the appropriate time, because once the trigger it will remain conducting. So AC sinusoidal circuit natural commutation occurs every half cycle. Then during the positive half cycle of the AC sinusoidal, thyristor is forward biased, in which anode positive and can be triggered on using the gate signal or the pulse. As we see in the diagram, the right hand side, the forward bias as it is in the on state. Now during the negative half cycle, the anode becomes negative while the cathode is positive. The thyristor is the reversed biased by this voltage and cannot conduct even if a gate signal is present. In this case, now applying the gate signal at a appropriate time during the positive half cycle of the AC waveform. Now we trigger it, then the thyristor can be triggered into a conduction until the end of the positive half cycle by using the gate signal. Thus, phase control can be used to trigger the thyristor at any point along the positive half of the AC waveform. And one of the many uses of the silicon control rectifier is in the power control of the AC system. As you see in the diagram, it is very clear from here, then how it is conducted, how is it triggered. This is the conduction point in the waveform. Sinusoidal wave is conduction form. Now you see here that it is a lamp load WAC SCR. Now we are trigger it in the at the higher side when it is the maximum. Then we trigger it when it is the next point. You see here the both the triggering conditions are shown here. Then it will conduct and we will off it. So we can adjust it accordingly. So at the start of the heat positive cycle, the SCR is of the is in the off state, and on the application of the gate pulse triggered of the SCR into the conduction, it remains fully latched the on state for the duration of the full positive cycle. So here if, at the starting it is on the off state, but if the for full cycle it is in the on state. Now, if the thyristor is triggered at the beginning of the half cycle, that is theta is equal to 0, the load will on for the full positive cycle of the AC waveform, as you see, and it is a half wave rectifier AC. That is why it is charged up to the half wave at the average voltage of the 0.3 into 0.318 into Vp. Now, as the application of the gate trigger pulse increases along with the half cycle 0 to 90, the lamp is illuminated for the less time, and the average voltage delivered to the lamp will also be proportionally less reduce its brightness. As you see here, now it is triggered at a one point, then the illumination is less. Lamp illumination is for the shorter time. Now then we can use a silicon control rectifier as a AC light dimmer, as well as in a variety of other AC power applications such as AC motor speed control, temperature control system, and power regulator circuit, etc. Thus far we have seen that a thyristor is essentially a half wave device that conducts in only the positive half cycle of the positive half cycle of the sinusoidal wave when the anode is positive, and blocks the current flow like a diode when the anode is negative, irrespective of the gate signal. So, but there is a more semiconductor devices available which can come under the banner of the thyristor that can conduct in the both the direction, full wave devices, or can turned off by the gate signal. So such devices are gate turn off thyristor, that is GTO, static induction thyristor, that is SITH, MOS control thyristors, MCT, silicon control switch, that is SCS, triode thyristors, TRIAC, and light activated thyristor, that is LAS, SCR to the name. These are the some of the thyristor which are available in a variety of voltage and current ratings, making them attractive for use in the application at a very high power levels in the many devices. Thank you very much.